Hi everyone, and welcome to Design Week 2023. I'm your host, Ulysses, and this is day one. Design Week is a 3-day virtual event where you will learn about embedded design tips and tricks on day one, securing the cloud on day 2, and on 3, technology in the wild, where you'll learn some demos that can help you along your journey. But before we get started, I'm going to pass it to Allison, who will explain to you how you can participate today.
Good morning, everyone. Thanks for joining us. We are currently live on YouTube, LinkedIn, and Facebook, so make sure you like, subscribe, follow, all of that on all of the above. If you have any questions that come up during our broadcast today, please feel free to drop them in the comments or leave us a chat, and we will try to get to them at the end. If we get through our broadcast today and you still have questions or something you want a little more detail on, please feel free to send us an email to livestream@microchip.com. We'll have one of our experts get back to you on there. You can also take a look at our Design Week webpage, where if you visit the On24 platform by clicking register, it'll take you to a ton more content provided from our engineers all over the world on a whole bunch of topics. So we have a lot in store for you today and over the next 2 days, but it doesn't end when our broadcasts are done here. We have a ton more content coming for you, and we'll see you at the end for questions. Back to you, Ulysses.
All right, thank you, Allison. So let's get started. Let me introduce my panel. To the left, I have JR.
Hello, Ulysses.
Hi, JR. Then we have Sridhar.
Hi, Ulysses and JR. Glad to be here.
And then at the very end, we have Ross. Hi, Ross.
Hi, Ulysses. Good to be here.
All right, awesome. And so the first question today is, what are the available building blocks that we can use to start a rapid prototyping project?
Yeah, great question. That's often the challenge at the beginning when you're starting to a design, is to gather the hardware building blocks that, when put together properly, would closely resemble your proof of concept that you'd like to put together. You want something meaningful. There's base boards that we have. We have a number of IoT-related boards that have built-in connectivity. This one happens to have the WFI32, which is a Wi-Fi SoC. Quite the workhorse we'll be demoing tomorrow on an HVAC application. Also, there's a number of these click boards. Most all of these main boards contain a microbus slot, a connector here with a standard form factor. Very useful for adding sensors to designs. This is air pressure, there's altitude, there's even connectivity. So if you wanted to add Bluetooth or Wi-Fi, and we'll see that in just a little bit, you have those boards that plug into, as I mentioned, a bunch of IoT boards. They have 8, 16, 32-bit. For those, we also have a number of what we call our Curiosity family. I'll defer to Sridhar to go over those.
Thanks, JR. Just to highlight, delving deep into a little more of what JR mentioned, we have what is known as a Curiosity platform to enable customers to start their development process. So what we have here are different style of Curiosity boards. The first one is a cost-effective Curiosity Nano platform, which is self-encompassing. It has a built-in onboard programming / debugging capability so that you don't have to connect an external program or a debugger. If you want a little more advanced version of these Curiosity, the next up is a Curiosity Pro platform, where we have a little more add-on capabilities in addition to what the Nano provides. And if you want to develop a full-fledged system-level application, we have what is known as the Curiosity Ultra platform boards. These are much more full-fledged in terms of they have expansion capabilities where you can add on, let's say, a 3-inch display or a 4-inch display, or you can also add on a wireless or a wired interface to make it much more system level. So one other point what I would also like to highlight is these boards do represent what Microchip offers as a total system solution, because they do come with components which Microchip provides, whether it be the microcontroller, the microprocessor, the analog components, the LDOs, the power amplifiers, and also the interface devices like the Ethernet interface device, a CAN transceiver, to that effect. So without further ado, what I would like to now pass off is to my colleague, Ross, who would be walking you through an entire development process using the Curiosity Nano platform, which is our entry-level, the cost-effective board. Over to you, Ross.
Thanks. So one of the first things that we need to do when we're starting to work with a new platform is often find some examples. And so we can do this in the case of MPLAB Discover here. And so if we can cut to my monitor, You can search through if you're looking for a particular part. So for example, I'm looking for the AVR 64DD32, which is what I have here, and we can then filter that, or we can also filter by the peripheral that we're using or any kind of keywords in the example that you're trying to set up. And so then the next thing, let's actually go to the demo here. And so to start with, we have the AVR 64DD32 Curiosity Nano, and this has an onboard programmer debugger. It has all of the I/O pins broken out. It also has a user LED and a user switch, so you can get up and running quite quickly, and of course it's breadboard friendly. Then we have this sensor here. It's a force sensor, and it's just a resistive type sensor. The harder you press on it, the more the resistance changes. And then of course we have the new Bluetooth module here, which is the RNBD451. And we're going to be sending printf strings straight across to the smartphone here via a USART connection to the Bluetooth here. And of course, the baseboard here is actually what ties it all together. And so now let's, by pressing on the sensor here, we can see it's actually taking readings. And I've set it up so that it's not going to spam the terminal if I hold down to a particular pressure. And so we can see it's maxing out at around 4,000, which is the limit of the 12-bit ADC on this. So the next part is, how did I do this? So I'll jump across to MPLAB X here. So the first thing is when you plug in the Curiosity Nano board, the kit window comes up here, and there's so we have the name. It also shows the picture of it, but we have a whole bunch of links here that are really useful. So we have code examples that we can bring up on GitHub. And then you can go through GitHub and search for what part you're using, or perhaps peripheral or any other keywords for your design. We also have the out-of-the-box code, and this is really useful for the first time you've played with something. There's 3 examples here. The first one sets up an LED blinking program, so super simple, and you can see, follow through the code and see what's going on there. The second one turns on the onboard LED when you press a button, which is that user button that I just mentioned before. And the third one, it actually sends counts and sends that through the UART, and then you can actually use our data visualizer as a terminal to see that. Then next, we have the hardware user guide. Now this thing is really useful. I highly recommend people bookmark this. So just bringing up so there's a hardware description that includes the pinout, because that's one of the first things that you're looking for when you're working with something. The next things that we're also, let's pop that, there we go. One of the next things we're also looking for is, what if you want to try and to do some low power, for example? And I think that's, here we go, on a Curiosity Nano, and then low power measurements. And so there's a small trace on there that you can cut and solder a header into, so that way you can actually go into sleep modes, and you can use your bench meter, or whether it's some other type of device to measure the current that your low power application is using. There's also a kit homepage, the schematics of the board, which is very useful when you're laying out your project. You can use those schematics to help get you up and running quite quickly. And of course, the star of the show usually is the datasheet. And so I already have the datasheet open in my PDF reader of choice. And so we also have some relevant tech briefs, because one of the biggest things that you struggle with when you're setting something up is, where do I find the documentation? Where do I find relevant tech briefs? And so this is all centrally located on Microchip's website. And so we're going to be using 2 tech briefs today. One is called TB3262, which is getting started with writing C code for AVR microcontrollers. And the second one is getting started with USART. And so it helps us get up and running really quickly. And for example, with the USART one, there are 3 different use cases that walk us through exactly what to do. So now, let's actually jump into the code. So the first thing, I'm going to only going to cover 2 peripherals here, because we have a on-demand video that covers how to do this in depth. So let's just jump to those peripherals. So the first one is setting up your clock. So whenever you start a new project, obviously you want to set up your clock. And as a sanity test, you really want to measure that clock to make sure it's what you think it's going to be. Because if you think your USART is 9600 and it turns out it's something else because your main clock was different, then you're going to have all sorts of problems. So by outputting the main clock, you can see what's going on and move forward in a logical progression. And so jumping back to this tech brief here, there's a really useful bit, because it covers things like setting, clearing, register bits, and it talks about using bit masks and group masks and also group configurations. Now these are human readable macros, so instead of saying 1 bit shift left 4 ORed with 1 bit shift left 6, you can actually use a human readable macro there that actually makes sense, and you can see what settings you're doing. So it makes it really easy to write, really easy to read, and really easy to debug. And one of the things we're covering here with the clock is setting up the clock, and these use configuration change protection, or CCP registers. And it just uses this macro here, protected write. And in this case, the register is main clock control A, and then the write to it is the current contents of the main clock control A. And we can see the macro here is clock control, that's our peripheral, clock select, that's the bit field that we're writing to. And this OSC ULP32K is the ultra low power internal 32 kilohertz oscillator. So it's quite easy to see what's actually going on here. So jumping back to MPLAB X, so all we've done here in my main clock control function is I have set up the OSC HF, which is the high frequency oscillator, and then I've also output the clock using the clock out. And the next thing I'm doing is I've actually cleared the prescaler enable because I want to use the full clock speed. And the final thing is I'm setting up the clock frequency, and that 4M, because we see clock control, again, is our peripheral. Frequency select is the bit field, and 4M stands for 4 megahertz. The final thing I do is I set my direction register for my clock out pin, and then we can measure the clock. And the next one I'm going to show you is setting up TCA, which is timer counter A, and the 0 is for instance 0, and we have 2 instances of TCA on this device. And so since I'm using the 4 megahertz clock, that means if we take the inverse of that, that's the period, and that's 250 nanoseconds. And then I've decided to use a clock divider of 2, and that's in the control A register. And so then that gives me a clock period of 500 nanoseconds. And in this project, I want to use a 1 millisecond timer. And this is kind of similar to the Arduino millis function. And the idea here is you just count the number of milliseconds since something last happened, and you can determine whether I'm going to change states or whether I'm going to jump into some different code or what I'm going to execute based on the amount of time passed. And so if I'm doing a 1 millisecond timer, I need to know how many times that 500 nanoseconds goes into 1 millisecond. And it happens to be a nice round 2000. And so we actually write that to the period register. I set it up in my normal mode. I set up an overflow because I'm using interrupts that trigger every 1 millisecond. And the final thing is I set up the clock select, which I mentioned before was divided by 2, and I enable it. And just to show you, so we have this macro here, single clock select div2 underscore GC, which stands for group configuration. And if I jump to the header file here, we can actually see here that same macro, TCA single clock select div2, is a 1 bit shift to the left by 1. And then if I come also down to my data sheet, this is the same register. So I have, come on, scroll up, there we go. So we have TCA is my peripheral. The register I'm writing to is control A, and it's control A there. The bit field is clock select, and of course the last thing is div2. So it's a very human readable way of setting things up and makes your life much, much easier.
All right, so Bluetooth drivers are hard to set up. Would you say this was difficult for you?
No, not at all. It uses a USART interface. And so as a result, this means I just connect my TX and RX pins. I set up my baud rate for this device. It's 115200. And then it just uses a pretty standard frame format of 8 data bits, no parity, 1 stop bit.
Awesome. And then more generally speaking, what are some common challenges an engineer might encounter when starting an embedded design?
So usually especially if you're starting with an ecosystem you're not familiar with, one of the hardest things is where do I find the documentation? And so part of that is you can find it very easily on the Microchip website, or as I showed before with the kit window here, you can get the data sheet straight through the kit window. You can then also go to our website and download any relevant tech briefs. And you can also search Microchip Discover, MPLAB Discover, as I was showing before. So you can search for something in there. And so, for example, I've searched for AVR64DD32, and there's a whole bunch of examples here. And one here is an agricultural IoT sensor node that uses this same part and also uses a LoRa module. And so there's a full write-up, there's full documentation, all the software that's used, the hardware that's used. This helps you really get up and running quite quickly.
All right, awesome. And then before we move on to software, I'd just like to show you my screen with, we have a lot of plug-and-play clipboards that are available for you guys. We have 176, so please check them out. It's with our partner. And now, would you like to
Yeah,
say something?
just to add to that,
Yes.
Microelectronica is a partner of ours. These boards can be purchased directly from MicroE, or since I'm from Minnesota, I buy mine on DigiKey because they come fast. But yeah, as Ulysses mentioned, there's hundreds of these, and you can find a huge array of different types of sensors, as well as connectivity. Like if you wanted to add Ethernet, for example, to one of the Curiosity boards, there are Ethernet clicks. There are Wi-Fi clicks, there are Bluetooth clicks, like what Ross has over there. So sensors, processing, and connectivity, as well as security too. You can add in our secure elements. We'll talk a little bit more about that tomorrow.
All right, thank you. And then Sridhar.
Just to add on to what my colleague Jim mentioned, the point is that the Curiosity Nano boards are small form factors. We do have some boards like the IoT board, which Jim mentioned, which does have the wireless connectivity. So if you want to add, let's say, an Ethernet connectivity to this platform, what we have is, as Ross was showing you, there is a Curiosity Nano expansion board. So there are options there to plug in an Ethernet micro board onto that, like as you see here. Or the Curiosity Pros, some of the Curiosity Pro / Ultra boards do come in with a built-in Ethernet interface, also including the transceivers. So that's an additional information.
All right, awesome. And now that we know what hardware to use, what sort of software can we use to begin and for advanced projects?
Okay, good question, Ulysses. As we all understand, silicon is important, but what surrounds the silicon, or the ecosystem as we call them, does make it more critical in a development process. So what I would like to highlight is the MPLAB, which is the ecosystem consisting of the integrated development environment, the compilers, the debuggers, the assembler, linker, does form the backbone of any development process. So to start off, when you have a silicon, it needs to be configured. So what we do have for that is a MPLAB code configurator. So when I say MPLAB code configurator, it helps you to configure the silicon, as Ross was mentioning, to a given application. So there are hundreds of registers to be programmed on the board. So what we would like to make it easy for your development process is to get it abstracted so that you don't have to go and remember these registers. So when you pop up the MPLAB code configurator, you have the register map for a given device, which would go and help you to set it up. So now, the nice thing about the MPLAB code configurator is it works across all the microcontroller platforms. So whether it is an 8-bit, 16-bit, 32-bit microcontroller, you do have the baseline MCC or MPLAB MCC, as we call it, to configure your device. The nice thing from a developer's perspective is you don't have to go and learn a new configuration tool every time you switch or every time your application need changes. So once you are familiar, let's say, with an AVR development, and you want and do a development using our 16-bit DSPIC or a 32-bit PIC or SAM microcontroller, the configuration tool still remains the same. So that is the one unifying tool from a configuration standpoint. So that kind of covers the silicon element of the development platform. Now, as you all know, silicons come with a lot of peripherals, be it the Ethernet, be it the USB, the CAN interfaces, the touch interfaces, and other things. So what we have done here is to ease the development process. We have two embedded software development frameworks. One is the MCC Melody, which supports the 8 and 16-bit microcontroller embedded, which acts as the software framework for 8 and 16-bit microcontrollers. Then we have the MPLAB Harmony, which is the embedded software development framework for 32-bit microcontrollers. wireless devices, the microprocessors, and so be it. So what this software development framework does is provides you the stacks or the software library, be it the USB library, the graphics library, the touch library, the TCP IP library, so that you can run them on the Microchip microcontrollers or microprocessors. The nice thing about this is, so long as you are using this in the development on any of our devices, it is free for your use, so that you're not have to go to pay to use this library. So that is the advantage what you get, and still it is all plug-in into the MPLAB ecosystem. So we covered the silicon and the peripherals associated with the silicon. So let us now get into the application development itself. So there are myriads of applications where our devices are used. So let me pick up a few where, like let's say you have a motor control application, be it an HVAC or any other class of application where you want to spin a motor. So when you are developing with DSPIC family of microcontrollers, let us say, so we do have what is known as a motor bench development suite. So this is a library that is used within the MPLAB toolchain to help motor control engineers develop their algorithms. So what happens here is within the motor bench development suite is a motor control application framework, which provides, again, within the MPLAB toolchain. So I would like to highlight that fact. And within the application framework is a different motion control APIs, which a customer would call, and then it provides the source code to implement your algorithm. It could be a single phase PMSM motor, it could be dual phase or a brushless DC motor, so be it. So the idea is for you to not worry about writing those individual algorithms, but take what is available, and so that it helps you speed up the development process. Similarly, when we look at the switch mode power supplies, with data centers proliferating, the AC to DC power supplies, and in the telecom industry, the DC to DC power supplies are ubiquitous, right? So to enable to write the digital signal processing code for these switch mode power supplies, we do have what is known as PowerSmart within the MPLAB toolchain. This eliminates the need for you to write a digital DSP code, which is fairly time consuming. So what we have done there is we have a digital control library designer, again within the MPLAB environment. This provides you an interface to implement the loops for switch mode power supplies. It also has a graphical interface for tuning, optimizing the system. So that covers the two application areas. So similarly, if you are using a 32-bit microcontroller for motor control development, we have what is known as QSpin, which provides you the user interface. There is also a user interface if you are developing a networking application and using the TCP IP stack. So we have these all these tools within the MPLAB ecosystem, which enables you to start and speed up your development process. So that is kind of a broad spectrum of the hardware development platforms, the software tools, the software development environment, the application libraries, and so on. So we tie all this together. The MPLAB ecosystem provides you the framework to tie all this together. And what I would now like is to ask my colleague Jim to walk you through what are the resources that are available for you and where you can find them and where you can learn things at your own pace and start your development process. Jim, over to you.
You bet. Thanks, Sridhar. That really tied the room together with the hardware and the software and everything that you can do. So I wanted to note that all of the recordings for the live streams are pinned to the top of our LinkedIn page and Twitter feed. So for any of these resources that you'd like to review afterwards, you can go back and view those recordings. In addition to that, we have Microchip University, and maybe we could pull that up. There we are. So Microchip University is a collection of free recorded classes. Some of them are instruction only. Some of them do have labs along with them. and along with the content that's available on GitHub, linked to it in the course. If you could scroll down a little further, you can see all the different areas we cover, from software frameworks, programmable logic FPGAs, Linux, there's connectivity, safety, security, Internet of Things. We have a whole section with connecting to Microsoft Azure, IoT, analog, motor control, and power management, as Sridhar mentioned. So there's a huge variety of different classes that you can take. There's over 100 classes that are available on demand. So Microchip University, mu.microchip.com is where you'd find that.
All right, awesome. And then we also have our new series called Ask Our Experts. It's our YouTube series where our experts answer frequently asked questions on a variety of topics. So check that out. And do we have any questions from the audience?
Yes, we have some questions. We'll go ahead and get started with this question from PLC Worker on YouTube. He's asking if Microchip has any Curiosity Nano boards with Ethernet capability.
The answer to that is yes, and they're available through, so Microchip supports Ethernet devices. We have some that are SPI-based Mac PHYs. We have 10BASE-T, 10100, 1 gig Ethernet, and we also have 10BASE T1S. Some of those are available from Micro E as a clipboard format. The PHYs themselves, of course, the layout in between the Mac and the PHY is not able to go through this interface here, just due to the signal integrity. But we do have standalone Ethernet solutions that are on clipboards that are made by Microelectronica.
Thanks, JR. I'll give you this next question as well. It's also coming from YouTube. This person's asking how we get info to a web page with or without wireless technology.
Yeah, good question. So some sort of connectivity would be necessary in order to get the bytes off the board and into the cloud. And we'll cover some of that tomorrow with the HVAC demo. For wireless, we have Wi-Fi and Bluetooth. Bluetooth, of course, talking to a smart device and up to the cloud. Ethernet can go natively as well over TCP/IP. And those are just some of the methods that one would get IoT data up to a cloud container.
Gotcha, thank you. This next question is for Ross in regards to your demo. This person's asking, when working with the newer RN-BD 451 versus the older RN 4870, what changes did you need to make for the project for it to work?
So the only change I actually needed to make was I needed to change this jumper from USB to being powered by the board, and that was it. The board rate is the same, the frame format was the same, it's a USART connection to it, so it's just TX and RX, there's no flow control, and it just works.
All right, thank you. This next question is for Sridhar. You mentioned MCC. Does it work across all MCUs?
Yeah, as I mentioned earlier on, the MCC is a configuration tool which works across 8, 16, 32-bit microcontrollers, to be very specific. So as your application needs changes, you can use the MCC to configure your device. Yes, so it does work across different microcontroller devices or platforms.
Thanks, Sridhar. All right, this next question I'll ask JR. In order to start developing quickly, what is the fastest and easiest way to start?
Yeah, great question, and it's something we really focus on at Microchip. We call it the mean time to meaningful. How quickly, what is the average mean time you can get to something that closely represents what you're trying to ultimately build in production? And so that first proof of concept, that first minimum viable product, be able to rapidly prototype using these smaller boards and piece them together, just like Ross has done over there. Not only the hardware, but then also the software, along with Microchip Discover that we've had that can be found at discover.microchip.com. With that, there's 1,700 different applications that have a really nice markdown description of what they are, how to use them, where to find further documentation. Also, as well, there's a drop-down with a project that you can go straight to GitHub and find the project at the Microchip Tech GitHub repository.
All right, thank you so much. That's going to wrap up our questions for today. If you have a question that we weren't able to get to or you think of something after, again, you can send us an email to livestream@microchip.com. We'll have someone get back to you there. We look forward to seeing you the next 2 days where we'll have lots of hands-on demos and more good information. So we'll see you tomorrow, and back to you, Ulysses.
All right, thank you. And then all of our live streaming courses are pinned at the top of our Twitter and LinkedIn feed, just to let you guys know. And as a reminder, to access all of our content throughout the day, just go to Design Week 2023 Microchip, click register. It'll take you to the On24 platform, where you will learn about basic concepts to keep your embedded C code from crashing, new data visualization features, and getting started with bare metal programming using 8-bit AVR MCUs, which is run by Ross. So that would be great. And as always, I'd like to thank my panel for being here. And
Thanks,
for the,
Ulysses.
yes,
Good to be
and
here,
for
thanks.
viewers for making this possible. And stay tuned for tomorrow, which is going to be about securing the cloud. And see you next time.
All right.